Leaks can be divided into three types: reported leakage, unreported leakage, and background leakage, according to their characteristics. Reported leakage that occurs on the surface is immediately detected by nearby residents, and rapid leakage repair is thus possible. The amount of leakage at the damaged area is larger than that of unreported leakage and background leakage. Unreported leakage is difficult to detect because leaks do not appear on the surface and therefore needs active leakage detection. The amount of leakage at the damage area is intermediate, occurring between the reported leakage and background leakage. Background leakage has similar characteristics to the unreported leakage, but it is difficult to detect leaks that occur at the joints and connection parts of pipelines with the conventional acoustic leak detection device. Therefore, water pressure management and pipeline replacement are required to reduce background leakage. What causes leaks? The causes of leaks in water supply facilities can be divided into internal factors caused by the aging and corrosion of pipes, poor design construction, and large fluctuations in water pressure inside the pipe. External factors are the result of traffic load increase, soil layer change, and external damage due to other works. Leaks occur due to the complex interaction between these various factors. Knowing that, let's look more closely at the specific causes of water leaks. Internal factors can be further subdivided. We find pipe materials-related factors, such as a decrease in strength due to corrosion and deterioration of materials due to long-term use, design and construction technology-related factors, which include design errors, poor connection at joints, improper embedment, contact with other structures, non-application of anti-corrosion methods and galvanic corrosion, dissimilar metal corrosion, and factors inside the pipe, such as changes in water pressure and quality, water hammer and temperature changes. External factors are subdivided into embedment environment-related factors, such as an increased traffic load, cavitation around the pipe due to leakage, movement of the ground, pipes bursting because of freezing, excessive external stress, and soil pollution due to industry wastewater and other works, disasters-related factors, which include external damage by other construction works, changes in the embedment environment as a result of other works, and damaged ground and roads due to earthquakes. Next, we will take a look at the leakage characteristics. The first lesson is about leakage response time. The most important thing in leakage management is to shorten the leak time as much as possible so as to reduce the overall amount of leakage. The duration of leakage is divided into leakage awareness, location, and repair time. To be more specific, the leakage awareness time refers to the time it takes to check the presence of leaks based on the minimum night flow analysis and other factors. After being aware of leakage, one needs to quickly pinpoint the location of the leaks and perform the necessary leak repairs. The required time varies depending on the leak detection and repair technologies, and the worker's proficiency levels. The amount of water loss due to leakage is proportional to the duration of leakage. That is, the amount of loss due to leakage increases as the duration of leakage increases. Let's take a look at the second leakage characteristics. Leaks occur due to the various causes described earlier. Reported leakage can be detected and repaired immediately to reduce leakage, but unreported leakage and background leakage will continue for a long time if leakage detection is not carried out. Even if unreported leakage and background leakage are repaired after their detection, new leaks may occur at the same point with the passage of time. This characteristic of leakage is called leakage restoration, and the success or failure of leakage management depends on how well we manage the leakage to be restored. Next, let's talk about the general matters concerning leakage detection. Basic procedures for leakage detection take plane, line, and point approaches. They are carried out sequentially as follows. The leakage area is selected based on an analysis of the revenue-water ratio for each block and the minimum night flow analysis. And the leakage section, pipeline, is then checked via a step test and acoustic valve leak detection. After that, the leakage point is identified by listening for leak noise from water taps and electronic leak detection. Let's go through the details step by step. The first step is plane approach. The plane approach is a method to select areas with a low revenue-water ratio and a lot of leakage based on an analysis of the revenue-water ratio for each block and the minimum night flow analysis, and to determine the area suspicious for water leaks. If the block system is not established, the suspected leakage area can be determined based on an analysis of the revenue-water ratio for each reservoir, the flow rate analysis of pipe networks, and water pressure measurement. The minimum night flow, MNF, of block or zone refers to the amount of water supply during the time at which the water use is at its lowest. It includes the amount of nighttime water use and water leakage. The amount of nighttime use consists of household toilet use, nighttime use in factories and hospitals, and large-scale nighttime use at apartment houses. The remaining quantity, excluding such used amounts, is estimated as the amount of leakage. Therefore, as shown in the following graph, if the minimum night flow in the block further increases compared to normal nighttime use, or if there is an abnormality, the relevant area, region, can be judged as a suspected leakage area. Next, let's look at the line approach. The line approach is a concept of approaching the leakage section, pipeline, among the areas suspicious for leaks discovered via the plane approach. It is a method for determining whether a leak is suspected in a specific section or a pipeline. Let's learn more about the step test. The step test is an effective flow-based leak detection method to pinpoint the suspected leakage section in a drainage network. In particular, this method is suitable for identifying a region with high leak rates and areas where leak sound is absorbed into the ground, and the existing acoustic leak detection methods are not effective. Meanwhile, inflow into the area needs to be monitored to perform a step test. The inflow entering the area can be measured using a data logger to automatically transmit flow data to the inflow meter. If this additional facility is not available, the operator can also manually record the flow rate and pipe network data at the place where the inflow meter is present. Once the monitoring method is established, The valves are closed on a step-by-step basis to block areas known as steps. This allows you to know how much water is supplied at each stage. Each step has a certain amount of use, and you can compare the flow rate drop in the inflow meter whenever the valve is shut off. If there is a significant decrease in flow rate at a certain step, it can be determined that a leak point is included in the step. Now let's learn about the step test procedures. When the step test is carried out, as preparatory work, the valve farthest from the inlet point is closed in stages to check the change of flow rates for each step, and thus to identify the leakage section. In the step isolation, if there is no change in water pressure, it is necessary to recheck the water pressure in the nearby areas and close the final inlet valve to confirm that the inflow rate is 0. After it is confirmed that the inflow rate is 0, it is necessary to open the valves in the reverse order, check the water pressure and water quality, and complete the work if it is good. Let's learn more about the step test implementation method and effects through actual step test cases. The water supply areas of Dong level, regions, and Sosan were divided into a total of 16 steps, and the flow rates for each step were measured using an electromagnetic flow meter installed at the inlet point of the water supply area. The valves on the pipelines in each section are closed one by one, reducing the size of the supply area, and the flow rate changes are then analyzed to derive the suspected leakage section. The following graph shows a decrease in flow rates as the steps, Step 1 through Step 16, proceed. It can be confirmed that the section of the suspected leak appears in Steps 6 and 8, where the flow rate decreases significantly. Meanwhile, Step 12 was excluded from the suspected leakage section because of the flow rate change resulting from the temporary valve opening. Leakage detection and repairs were conducted on the water supply area judged to be the section of the suspected leak through the step test. As a result, the minimum night flow was reduced from 43 cubic meters per hour to 4 cubic meters per hour. When planning the step test, it is important to determine which pipes to use for each area, which valves to close, and in what order to close the valves. In addition, the order in which the step test is conducted should not be changed if possible, and the step test plan should be usable in leakage detection after the step test or subsequent step test. Keeping the plan consistent will be helpful in analyzing the effects before and after the step test, leakage detection, and repairs. In addition, it is important to establish the optimal number of steps when planning the step test. The number of steps depends on the size of the area. If the number of steps is too few, the detection area will be too large to achieve the savings goal, given the detection time and costs in the future. Conversely, it is too large. A lot of time is required for the step test, and the amount of leakage for each step may be too small to measure with a flow meter. Another consideration for step test planning is to estimate the consumer use so that the network operator can know the normal flow rate entering the step area. If a step test is conducted without estimating consumer use, it becomes difficult to distinguish between consumer use and leakage. In addition, the step test should be done when demand is at its lowest. It is usually performed at nighttime between 1 o'clock and 4 o'clock, which helps the step test be more accurate while minimizing any change due to demand. Lastly, the positions of all necessary valves should be confirmed on site before the step test. Once the location is verified, it is necessary to check if the valve is accessible and the valve and water stop are available. The zero pressure test is to test whether the valve can be completely closed to stop the flow of water, and it is needed to perform an accurate and stable step test. At each step, simple water pressure test gauges are installed to check whether the water pressure is zero. There are two methods to check the flow data while closing the valve in the pipe network. The first method is for a flow meter operator to communicate the flow data to other operators who operate valves in the pipe network via telephone radio communication. And the second method is for an operator at the site to check the flow data through a data logger that sends the flow data to an appropriate receiver so as to view the flow data in real time. There are three types of valves when a step test is carried out. The first type of valve is normally closed to form a zone and is called a boundary valve or zone valve. The second type of valve needs to be closed to form a step prior to the start of the test and is usually referred to as a single valve. However, closing only one valve cannot block the entire section in some cases. The third type of valve is to isolate the step from the zone. The valves which fall into this category are numbered sequentially and closed in sequence during the test. The valve in the first step is usually farthest from the flow meter, while the valve in the last step is closest to the flow meter. It is important to set the closing time for each step to approximately 10 to 15 minutes so as to obtain stable flow data. In addition, it is necessary to record all procedures, including valve lockout. Lastly, let's talk about the point approach. The point approach is a method to check the leak point through valves and water faucets, road listening surveys, or correlation leak detection for the confirmed section of suspected leakage. If the section of the suspected leak is selected, leakage detection is done in the following manner. Water leaking from water pipes flows into the soil around the pipe, which causes the pipe and soil in the leaking part to vibrate. The sound and vibration is transmitted by the pipeline, structure transmission, the material around the pipeline, ground transmission, and the water itself within a certain frequency range. Leak sound travels much better through hard material, and it travels farther along a metal pipe than the plastic one. In addition, although the ground is generally not good as a transmission path of a leak sound, if the distance from the surface is short, the leak sound is easily transmitted to the ground surface. Meanwhile, leak sounds are better transmitted through high water pressure, hard backfill, small bursts, metal pipes, and small diameter pipes. Conversely, it is relatively difficult for low water pressure, soft backfill, cracked main pipes, soft and lined pipes, and large diameter pipes to transmit leak sound. Devices for detecting leaks include simple listening rods, an electronic leak detector, and correlation leak detectors. Let's take a closer look at them. First, the simple listening rod is the device widely used by water service providers, and it can be said to be the most basic equipment for leakage detection. The materials of the listening rod include metal, wood, or plastic, though metal is mainly used as the material. The effectiveness of this method depends greatly on the leak investigator's experience and ability to listen for a leak, and a separate electronic device that amplifies the sound is not used in this method. The structure of a listening rod is as follows. To find the location of leaks, one needs to put the lower end of the rod against the joint, valve, etc., or water faucet, meter, of the pipeline at the point where the leakage is suspected, and listen to the leak sound through the part where one puts the ear on the top to determine whether there is a leak. This method is most suitable for use on metal pipes with a diameter of 75 millimeters to 250 millimeters. When leakage detection is done using a simple listening rod, the type of leakage, soil backfill, pressure of water leaking from the pipe, and ambient noise should also be considered along with the pipe material and pipe diameter. Let's take a look at the electronic leak detector. The disadvantage of using a simple listening rod for leakage detection is that a leak investigator has to rely on his hearing, experience, and skills. However, it should be noted that not all leaks can be heard by the human ear. Contrary to popular belief, loud leak sounds don't always mean there are large volume leaks. Sometimes, a large crack in the pipe often produces a smaller leak sound than that from a small hole, as in the cases of PVC and PE pipes. Therefore, in a situation where non-metallic pipes are increasingly used in pipe networks, it is more effective to use an electroacoustic microphone to amplify the leak sound for leakage detection. The electronic leak detector consists of a main body, signal amplification and display device, headphones, and pickup sensor. Its principle is similar to that of the listening rod, but it differs in that the signal of a small leak sound that is difficult to hear directly with human ears is detected using the pickup sensor, and the body electrically amplifies the signal to determine whether there is a leak with sound through the headphones. The electronic leak detector is a method to detect leak sound transmitted to the road surface due to leaks from the water supply and drain pipes on the road, and it is thus greatly affected by sound from consumer water use and traffic. Therefore, leakage detection is usually done at night. The leak investigator moves along the pipeline and locates a leak, while repeating acoustic detection until he finds the largest leak sound. Even if he finds the location of a leak, he is required to listen to the leak sound around the location again to find a more accurate leak location and thus to reduce the number of leak detection errors. Lastly, let's take a look at the correlation leak detector. The correlation leak detector consists of two data loggers and a correlator, laptop, and program. In the case of multi-point correlation leak detectors, multiple data loggers are installed simultaneously to detect leaks from complex pipelines at the same time. First, A data logger is installed at the pipeline facilities, pipelines, valves, in the area of suspected leakage to collect the leak sound. Then, the pipeline information, pipe type, diameter, length, is entered into the correlator, and the distance between each data logger and leak point is calculated based on the distance between the propagation speed of the leak sound and the arrival time to the data logger to identify the location of the leak. In the following figure, L is the distance between the sensors. LB, LA are the distances from the leak points to the sensors, respectively, and C is the transmission speed of the leak sound. The time it takes for the leak sound generated at the leak point P to reach points A and B is as follows. The equation for the transmission time difference is shown below. It can then be represented as a value of LB as follows. Meanwhile, the distance between each sensor is, and thus becomes. This can, in turn, be summarized as in. Therefore, the distance, LA, from point A to leak point is as follows. Here, C is obtained by the theoretical equation such as pressure wave propagation speed from water hammer. A fundamental understanding of the layout of pipe networks is needed to use the correlation leak detector. For example, as shown in the following figure, if there are no leaks in the section D, where a sensor is installed, and leaks occur in the external point outside the sensor A, water leaks are assumed to occur in the sensor A. In this case, you need to move the sensor to the suspected leakage section to detect the leak. In addition, the installation distance between data loggers should not exceed 200 meters. When you enter pipe information, there may be errors in the pipe type, pipe diameter, and length values, and the transmission speed of leak sound may also vary depending on the deterioration degree of the pipeline. The area where there is a similar leak sound from fixed sound sources, such as a transformer, requires particular attention to data analysis. In order to find an exact leak point, the correlation leak detector should be used in parallel with the electronic leak detector. Let's take a brief look at the noise logger. The leak noise has a more consistent and loud sound characteristic compared to other sounds, and the noise logger is a device to detect this leak noise. The noise logger is generally set to operate primarily during nighttime, when noise that interferes with leak sound, collection, traffic, water use is minimized, and leak noise is most easily detected. Its operating hours can be changed at any time depending on leak conditions. The noise logger is comprised of multiple acoustic wave loggers and signal receivers. The acoustic wave loggers are installed in places exposed to pipelines, such as underground fire hydrants or valves to collect sound for a set period of time. The acoustic wave logger should be installed vertically if possible. The distance between acoustic wave loggers should be less than 200 meters. In the case of non-metallic pipes, the installation interval of the acoustic wave logger should be less than 50 meters at the maximum. The collected data is transmitted by wireless signal, or the leak detector collects the data directly as it moves along the installation location of the acoustic wave logger. The place with noise above the minimum noise level is selected as a suspected leak point, where the leakage detection is carried out to locate leaks. The noise logger comes in various types, such as portable and fixed loggers. In particular, the portable noise logger is a method of detecting leaks with a high-sensitivity leak detection sensor. which has a wireless communication function installed in the waterworks pipeline and water taps. The leak detection sensor is installed to directly contact the water pipe as the same location as the valve in the meter box. If a leak occurs around the water pipe with the sensor attached, a slight leak sound arises from the leakage area. This sound is converted into an electric signal in a vibration transducer inside the sensor along the water pipe in the form of minute vibration, and data is transmitted to the manager server leakage monitoring program through wireless communication via a wireless communication module installed in the sensor. The leak monitoring program analyzes the amplitude and frequency of vibrations and allows you to check for the occurrence of leaks, suspicion of leaks, and normal status on the screen. Let me illustrate the effects of the portable noise logger through the case of Taeangun. Taeangun does not have its own water treatment plant and uses all of its water from the metropolitan water supply system of the Boryong Dam. In 2014, the revenue water ratio was 65%, and therefore there was an urgent need to reduce leakage. Particularly in Cheonjung-ni, Taeangun, a leakage problem was serious, but it was not easy to detect the leakage due to the noise of the surrounding area, such as the sound of waves at the shoreline. In addition, the leakage did not rise above the ground made of gravel and sandy soil, which makes it difficult to detect leaks. Thus, 200 noise loggers were installed at water taps, and the logger was moved and installed repeatedly to maximize leak monitoring efficiency. As a result of the leakage detection, 30 leak cases were found, and through the leakage repair work, the minimum night flow decreased by 46 cubic meters per hour, from 74 cubic meters per hour to 28 cubic meters per hour, reducing the leakage of 1,104 cubic meters per day. The following figure compares the number of leak points before and after leakage repairs in Cheonjung-ni, Taeangun. Let's continue with the step test. The step test is the process of closing the valves in a certain section within the small block, step by step, during the time of minimum nighttime use, and measuring the flow rate change at the inlet point to determine whether leaks occur in each unit section, and if there is a problematic pipeline. It can also be checked whether the old pipe is connected or not through simple water pressure measurement to confirm step isolation. The step test is applied to the block system establishment or section isolation, balancing system pipe network areas, and small-scale water supply area supplied to single inlet points, or an area that enables conversion supply to a single inlet point. Also, at the inlet point, a facility capable of measuring the flow rate every minute at the unit of L per minute should be installed, and it should be possible to conduct the flow valve logging, display, or remote monitoring. Next, let's talk about the step test types. The step test types are divided into the full isolation method and partial isolation method. Now let's go into further detail. The full isolation method is a method of closing valves in stages from the farthest point of the block inlet point to shut off the valve at the final inlet point, confirming that the inflow rate becomes zero, and then opening the closed valve in the reverse order. This way, the step-by-step valve lockout eliminates the consumer's water use at night, and a more accurate test can be carried out. In addition, it facilitates the identification of the current status of water leakage for the entire block, block isolation, and pipeline connection within the block, but may cause long-term suspension of the water supply to consumers and turbid water. In particular, drain and air exhaust work is necessary when water is discharged. In general, the full isolation method is recommended for areas where the pipeline status is not accurately identified. The partial isolation method is to close the valves one step at a time for a certain section within the block, measuring the flow rate change and then reopen them. This method has the advantages of minimizing the suspension of water supply to consumers, generation of turbid water and air influx. However, accurate analysis is difficult when there is a lot of water use at night, or fluctuations are severe. In addition, it should not be applied in areas where the pipeline status is not accurately identified because it is highly likely to fail as the valves are closed or opened step by step. Here's the work process of the step test. The step test is carried out in the order of field survey, work plan establishment, publicity and notification, step test execution, and data organization and analysis. Let's take a look at the details of each step. The field survey is to collect basic data for planning and should be completed about 1 week prior to the step test. The geographic information system, which includes information on water supply facilities, important consumer information, and other facility information, should be prepared for the field survey. In addition, it is necessary to measure the flow rate for about a week before the step test to investigate the current status of the minimum night flow and formation time. However, omission is possible if there is recently collected data. Next, in relation to the operational status of gate valve, drain valve, air valve and fire hydrant, valve accessibility, valve operation, and block and water pressure management area boundary valve, listening should be checked in advance and displayed in the drawing. In addition, problems need to be addressed immediately. A survey of large and special consumers is to investigate the effects of the suspension of water supply during the step test. The meter location, shutoff, gate valve position, and operational status, water use type and nighttime water use, and emergency supply plan for cases where water use at night is absolutely necessary are examined and displayed in the drawing. This is to select a location for measuring water pressure to check the isolation status of the step test. In general, it is necessary to select a location that satisfies the particulars of the hydrants and exposed outdoor faucets, measure water pressure and mark the results on the drawing. In this connection, the hydrant should be selected as a top priority, but the outdoor faucet can be selected if there is no hydrant. However, the outdoor faucet should be supplied with direct water, and the supply of direct water is checked by opening the faucet and watching a flow indicator on the meter rotate. If there are no hydrants or exposed outdoor faucets, a meter can be selected. However, the meter should be exposed outdoors and easily accessible. In principle, the location of water pressure measurement should be one for each step. However, one or two locations are additionally selected if the current status of the pipeline is not clear, because of suspicion of an old pipe connection. In addition, civil complaints may arise in relation to the exposed outdoor faucets and meters. Sufficient explanation is therefore required in advance. After the completion of the step test, it is necessary to check a location for confirming water pressure and water quality at the pipe ends and highlands. The main locations for confirmation include pipe ends, highlands, and areas with habitual poor discharge and red water. After the field survey is completed, a work plan is established. First is step selection. The step should be selected considering the block size and water supply and pipe network conditions based on the field survey. As main considerations, the step is divided based on the drain pipeline, gate valve, but not narrowly split. However, the section where severe leakage is expected needs to be subdivided. The number of steps should be around 10, and the maximum should not exceed 15 steps. In addition, it is necessary to select less than 20 gate valves for operation. If the embedment year and pipe type are the same, it is divided into one step. If there is a consumer that requires water use at night, such as a hospital or a factory, it is excluded from the step test. When there is a small pressurization facility, it should be excluded from the step test or switched to natural bypass flow. Once the step selection is completed, a work plan is established. The work plan is to establish a general work plan for the step test, such as the determination of step sequence, the sequence and time of valve operation, the determination of water pressure check location, water flow plan, drain plan, the confirmation of hydraulic restoration, and personnel composition based on the field survey and step selection. In the case of full isolation, the order of steps is planned sequentially from the step farthest from the inlet flow meter toward the inlet flow meter. On the other hand, in the case of partial isolation, the sequence of steps is planned so that the neighboring area does not suffer a suspension of water supply during the step isolation. The work plan is made by referring to the step test record, according to the step test execution flowchart. The work time is determined to be 0 to 4 before and after 2 hours, a total of 4 hours, based on the time of minimum night flow. However, if it is difficult to complete the work within 4 hours due to too many valve operation points and steps, the number of steps can be adjusted to make the work easier. It is important to maintain isolation for at least 5 to 10 minutes, even after the confirmation of step isolation, in order to stabilize the flow rate, and to keep it for at least 5 minutes after the valve operation so as not to generate red water due to sudden valve operation during the step recovery. If there is a small pressurization facility in the step test section, it should be planned to switch to bypass control or stop pressurization. If the step test section has a pipe network which takes the form of a loop, it should be planned to close the circulation valve in advance so as to minimize the test time. In principle, one location for each step is selected as a location for water pressure measurement based on the field survey, but 1 to 2 locations can be additionally selected if the current status of the pipeline is inaccurate due to a suspicion of an old pipe connection. After the completion of the step test, a location should be selected for the final confirmation of water pressure and water quality at pipe ends and highlands. And the personnel consists of 4 basic teams dealing with the overall situation. 2 people. Valve operation, 2 people. Water pressure check, 2 people. Civil complaints, 2 people. And an additional support team is formed considering the number of steps. After the work plan is established in this way, a geographic information system to be used for the step test is prepared based on the field survey contents, and it includes information about water supply facilities, important consumers, step test, and other facilities. Next, the task is to prepare the necessary equipment for the step test in advance. After the work plan is established, the step test plan should be publicized and notified to internal and external stakeholders influenced by the step test. The main subjects are short note promotion to consumers, notification to relevant organizations, and notification to any person in charge. The step test is carried out after publicity and notification. Because the step test is done at night, the operation valve position, water pressure measurement position, and flow rate measurement should be checked in advance during the day. In addition, protective facilities for parking prevention should be installed at the location of the gate valve to be operated. First, the gate valve is checked. The on-site investigation is performed in the order of the gate valve that operates during the step test. And safety facilities are installed to prevent parking. If the valve operator has no knowledge of the pipeline status, a number is marked on the valve position. The next step is to check the location of the water pressure measurement. The on-site investigation is carried out in the order of the water pressure measurement location to confirm step isolation. When water pressure is checked at the indoor faucet, a rubber hose is installed in advance to expose it to the outdoors. Also, in order to minimize civil complaints, due to water pressure measurement, sufficient explanation is given to the consumers in advance. The locations of pipe ends and highlands are checked to identify the location of the hydrant to check the water pressure and water quality at the pipe ends and highlands. The last step is to confirm the flow rate measurement. The flow rate measurement interval is set to 1 minute, and the unit is changed to L per minute to check whether the measurement is properly done. After the pre-work is completed, all workers gather in the control room 2 hours before the start of the step test. Listen to explanations about the work plan and schedule, check the personnel and task division, receive safety training, identify equipment and communication system, and they are then deployed on site. Next comes the prior valve operation. The worker is required to listen for leaks after operating the large consumer inlet valve at the scheduled time, and then report the operation time, number of rotations, and presence of leak to the control team. Major prior valve operations include large consumer inlet valve, circulation valve, pressurization plant shutdown, or bypass openings. Now is the time for a step test. The valve operation and water pressure are checked step by step according to the pre-scheduled time. The major precautions are that first, the control team should instruct and record all matters relating to valve operation, water pressure measurement, and worker movement. And the valve operation team and the water pressure check team should then follow the instructions of the control team. In addition, the valve operation team should report the operation time, number of rotations, and leaks to the control team after the valve operation. and the water pressure check team should measure the water pressure before and after the valve operation and report the results to the control team. Depending on the terrain conditions, the water pressure may not change immediately after step isolation. Therefore, measurements should be done after draining if necessary, and the isolation should be maintained for at least 5 to 10 minutes after the confirmation of step isolation. In the step recovery process, the valve operation should be in accordance with the instructions of the control team, and it should also be in operation for at least 5 minutes to prevent any red water phenomenon from occurring. When performing draining above water quality and water pressure levels during step recovery, the drain time, start, stop, should be recoded, and the final water pressure and quality should be checked at the pipe ends and in the highlands after the completion of the step test. In addition, there is a need to make preparations for civil complaints. After the completion of the step test, data needs to be organized and analyzed. The flow rate fluctuations at each step should be analyzed using the valve operation time and flow data for each step. In addition, the current status of pipelines and water taps at each step are used to analyze the estimated leakage and suspected leakage section for each step, organize problematic pipelines including old pipes, and make decisions to replace pipelines in connection with leaks, pipe types, and construction year. In addition, it is necessary to perform leakage detection and repairs immediately after the step test. Compare the estimated leakage and actual leakage, minimum night flow before and after leakage repairs, and conduct a comparative analysis among the calculated unreported bursts and background leakage within the block. Lastly, the analysis results should be used for future pipe network operation. 7 days before the step test, the department in charge and the local administrative welfare center in Kunsan City are informed of a plan for the suspension of water supply, and the administrative welfare center in turn informs consumers of the water supply suspension plan with the use of broadcast facilities. In addition, banners are installed around the areas where the suspension of water supply is expected so that the consumers can check the water supply suspension schedule. 1 day prior to the step test, banners are posted and active publicity is carried out to inform as many consumers as possible of the water supply suspension plan. On the day of the step test, workers gather at the office to check the division of labor and receive safety training. On the day of the step test, the position of the valve is checked and marked. In addition, the operation of the belt is checked, and a previous notice for parking prohibition is given. A mobile messenger group chat room is created to share work instructions and situations. Workers gather at the office and participate in a pre-meeting to discuss whether there is any abnormality before the work begins. Workers move to the site according to the division of labor, stop the pressurization plant, and suspend the water supply to the consumers. The isolation status is checked for each step. The workers perform drain cleaning according to the instructions and check turbid water.